All right, what's going on? For anybody who is here, thank you for stopping by. I'm going to go ahead and hook up the Chipwhisperer device here. Take it out of this little package. All right, here is the Chipwhisperer Nano device. I'm going to go ahead and plug it in to my machine. I'm on a MacBook Pro with an M1 processor, 16 gigabytes of RAM, 1 terabyte of hard disk space. And let's see, I'm gonna pull up some environments here to work in. The first one will be Perplexity. Going to navigate to Side Channel Analysis version 2. This is the project that I've decided to work in Perplexity. I created it recently, and there are instructions in this Perplexity project that I want this space to follow as I interact with it and the lab that I'm working on. And it's a Chipwhisperer lab. Looking for my water. Appreciate the likes. Thank you for stopping by, guys. All right, I trust that this Perplexity space was set up. That's quite an extensive rule set that we have here. I'm going to ask it to explain what its purpose is. Explain to me what your purpose is per the instructions that you have for this Perplexity project space. So here's what's brilliant that I'm working on. I'm building a laboratory environment, and I'm using Perplexity as well as, perhaps not yet, I haven't done it yet, but at some point I will be using Codex and Claude to actually build this studio environment, this laboratory environment that I'm in the process of building. And so I'm working with Perplexity to build it, and here's how we're working together. I've asked Perplexity, based on the instructions that I've given it, what its role is, and its response to me is that it says, I am here to help you run and understand the nano side channel analysis labs reliably. Preserve a truthful, reproducible record of what had happened during that lab experiment, and convert genuine learning / setup friction into a validated product insight for Trace Studio, which is the environment that I'm building. And it's brilliant. It's brilliant because I'm scraping real-time data from my experience so that I can build a product that solves any friction that I have to optimize learning opportunities. Let's begin with working on this project, starting with hooking up the Chipwhisperer device. It is now hooked up, and I am now going to run the commands that allow me to even perform the experiments in the first place. These are critical commands because they allow me to run the project, and this should be considered a product insight because we need to know how other users will need to set up their environments as well. All right, so let's get up that terminal. We're only in the terminal for a short moment. It doesn't really take us long to get out of the terminal environment. I am now starting the Chipwhisperer lab experiment and would like to proceed with exchanging information about the experience that I have and also interacting with the browser assistant. Your job as a browser assistant is to provide helpful insight for the main Perplexity project space agent so that we could design Trace Studios to address the product signals that we discovered through the friction points of working on this lab. What's up? Thanks for stopping by, you guys. Appreciate you visiting. I'm working on deciphering encryption keys on a hardware platform called the Chipwhisperer Nano. I've got it hooked up. I've launched the Python environment, and now I'm working with Perplexity to basically observe the experience that I have going through this lab. I think I'm going to change the name of this stream to like breaking encryption. Alright, so I changed the name of the stream to Deciphering AES128 Encryption Keys, AI Security. Perplexity AI, Vibe Coding Encryption, AES128. Refresh the page and see the new title. I think it's a good one. Okay, so Perplexity says, think of me as a lab partner. Think of me as a lab partner. Looking over your shoulder at the same screen. I can only tell you what I actually see or what you show me. I won't make stuff up about what your code did. When something feels annoying or confusing in the lab, I'll write it down in a way that helps build a better tool for next time. I have now arrived to the course folder that is located within the Chipwhisperer directory, and inside of the course folder is a SCA 201 folder, which has the lab that we'll be working on, which is CPA on 32-bit AES, and we will be starting with the hardware notebook since we are using a real hardware device, and then we'll use the CPA on 32-bit AES Python notebook lab 2_1. But I do want to consider that Trace Studios should also include a simulated type of experience as well, which looks like something that this lab course has to offer. Okay, so let's go ahead and dive into the hardware notebook here. Provide me with a sufficient passover report that I can give now that I'm working in a new browser tab with a new assistant once I open the notebook. All right, so we are working in the hardware notebook right now of the laboratory. In all capital letters, it says hardware. That indicates that this notebook is something that is required for us to follow, or it is highly suggested to look at this document if you are using a physical hardware device like this. The topic for today is correlation power analysis attack on 32-bit advanced encryption system we are in the hardware notebook. So use this run block down here, which traverses through the directories back to setup scripts, and then it calls this Python notebook setup generic. Now, setup generic is a file, a Python notebook in the directory that sets up the hardware for your device. So this run block is essential. This is a product signal. The run block is required to establish a connection to the hardware device that is being used. Can you explain if I have a misinterpretation of what this is for? How essential is the information that is contained within the setup generic Python notebook for product insight or signal? Should the contents of that notebook be recorded at this stage in not only product discovery, but for completing the lab? Because I just want to get this lab over with, but as much as I want to get it over with, I want to scrape this experience for friction points anywhere that I feel like there's a learning opportunity to understand what's going on within Jupyter Notebooks, how to use Jupyter Notebooks, within Chipwhisperer, how to use Chipwhisperer. I want to identify the friction points in that learning experience so that those friction points can be minimized and learning opportunities can be optimized. I want to start using the Claude CLI or Codex CLI for assisting with making modifications to the existing documents that define what Trace Studios is supposed to be. And so I would like to use Claude CLI or Codex CLI, whatever you suggest, or a combination of the two, in order to properly scaffold Trace Studios. And just as a refresh, the idea behind Trace Studios is right now to collect information regarding the experience that I have as a student who is learning about Chipwhisperer, and go through the existing lab modules and document my experience and identify friction points and product signals that could be used for scaffolding a vision for Trace Studios, which is a brilliant idea. It needs to be understood by the Perplexity instruction set for this project space that the main purpose for each context window is to assist me, the human, in working with all of these different components, such as the CLI for Codex and Claude, in addition to all of the browser assistant sessions that appear when navigating to different browser views. All of this information will be collected in the form of screenshots, in the form of Passover markdown files from the agents. And so this Perplexity space is the high-level orchestrator that needs to understand that all of these other systems are producing output, and this Perplexity project space needs to be prepared to receive all of those different outputs from the different AI systems that the user's interacting with, so that we can properly work with each of those systems. So that's what this Perplexity space needs to have ingrained in the settings as a list of instructions to follow. So please revise the current Perplexity instruction settings such that this goal has been achieved. That was lengthy. I hope it's got its high reasoning model on to understand that. Well, I would like the Codex and Claude agents to be responsible for interacting with the GitHub commands and pulling and pushing changes in the code. And so if using a GitHub journal fits into that workflow, then I'm cool with that. Now, this needs to fit within 8,000 characters because that is the limit for the settings instructions. Let's begin. What should I do next? We are working on lab 2_1 correlation power analysis on 32-bit AES. We are currently in the hardware notebook, and we have a browser assistant working with us currently. Is it possible to ask Codex or Claude CLI to do that for us? Please recommend an agent and model that I should use for this task with regards to Codex or Claude. Should I use Sonnet 5 or Opus 5, and what reasoning effort? Please make sure to include the provider as well as the specific model with regards to its reasoning strength for every single prompt that we paste into Claude or Codex. Just provide me with the entire prompt so I can copy and paste it into the CLI. All right, guys. Thank you for stopping by. We got Opus 5 working overtime right now for us. Opus 5 is going strong, scampering around, trying to find some information about the Nano, the Chipwhisperer, the device that we are using to break AES128 bit length encryption. Exciting times. And we're building a tool that is designed to minimize friction points in my own learning experience, and through that process I think we will create something brilliant. Now I have a taco in my hand. I'm going to eat it, so I'm going to turn my camera off for a minute and then I'll turn it back on. But I know some of you will just miss me so much, so that's why I'm letting you know. All right, I'm back. Don't worry. All right, so what's up, everybody? Thank you for stopping by. Please like this stream. It helps out a lot. That's what I've learned recently through watching YouTube videos on growing a YouTube. Impressions as well, and then how many I have, like 200,000 impressions, but my click-through ratio is like 5%. So I don't think my long form videos are very good. I'll spend some amount of effort that feels equivalent to making like a short, but it's like a longer short. I had a whole video that I broke up into 3 videos. Those are my most recent 3 videos. Instead of like posting it all as one video, I sort of broke it up into 3 parts. So that was sort of the intention there, was to build a music player and then have some kind of content that I can push over the next like couple days. Like I already finished the video, but now I'm just gonna split it up into 3, so that way I can post the first one, then the next one, then the next one. All right. What are we doing? Are we waiting for Claude, or are we forming this experiment? All right, Claude is almost done, but I want to know what we plan to do with the information that it gives us. I'm ready to start working on this lab experiment and performing the side channel analysis technique to break AES. I think I need to include a picture of myself in the thumbnail. I think maybe that's one thing I'm not doing that I could be doing to make it more enticing. I guess, I don't know. Or should I keep a picture of me off there? Because that was sort of the general idea from the very beginning. Man, this thing just keeps pumping out text. All right, so we got to wait for Claude's report, then paste it into the complete final report here. Ugh, that's so annoying. I don't want to do that, really. Okay, but moving forward, I just want you to know that I should have a prompt at the end to provide Claude or Codex, or should I work with Claude or Codex interactively during the entire lab, or should I just provide a report to the agents The main idea is for them to start modifying and editing the markdown files, such as the architecture and the glossary, and helping fulfill with the vision that is crafted through those documents, so that later on we can actually build the product of Trace Studios. Okay. Stop. I'm going to just start performing the experience and share it with you. We don't need Claude to do anything for us right now. I'm the boss, not you, AI. Understood. We'll stop. Okay. We're going to run this script. See that star? That means it's running. Aha. Well. Platform. Interesting. I don't know. I don't know what's going on. I'm going to restart the kernel. Well, it found the Chipwhisperer. You see, there's that info message there. So that's what we wanted, but something happened. I received the following error, but just after the info found Chipwhisperer message popped up. Just switching up the music here. So can you decrypt a string and reveal the pass phrase or show message without pass phrase? Yes. Yes. Decryption of an AES 128 bit length key. That key can be deciphered through evaluating power signals, and with a small leakage that occurs, you can identify a small, if you can identify a small leak in the power trace, leak of information, you can then use that leak to extract the full AES 128 bit length key. Well, it's sort of like more of a theory right now, you know, for your comment, just because we're having a conversation about it. To actually implement that would require, you know, setting up the firmware and building it out. So setting up a string, you know, some kind of string value. That is all something that can be performed using this hardware device. I am currently following a lab that is performing correlation power analysis. And let's see, the name of this is, so we're using the 32-bit processor on this device. It's a microcontroller. It's the part of the board that performs the encryption. And we're measuring that board with the other scope board. I'm just following along in this laboratory, so I'm not gonna like explore other ideas about encryption at this time, just because I'm trying to navigate through this directory of course lab modules. Decrypt message now. Okay, send me a, I mean, it's got to be encrypted with AES. That'd be, I'll tell you what, I'd like to do that for you. I'd like to set something like that up. But I'm a beginner, I'm a learner, I'm new, I'm not like trying to claim subject matter expertise here. I'm trying a little bit to grow the channel, so some of my titles and thumbnails, you know, I'm exploring some of those ideas where you get a higher CDR click-through ratio. So it is AES. It is AES. Yeah, this is performing AES. I could perform RSA. 256 is a different story, my friend. We are not doing 256. We are doing 128, not 256. Alright, so this should, I don't know why this error is happening. I'm going to unplug the device because this typically doesn't happen. And I turned the text really big just so it could be seen, but it's harder for me to really understand from that view. So I ran, it finds it. Do not run that cell yet until you confirm you want to declare nano configuration for the direct notebook. It does not touch the hardware. Can do either 128 or 256. What can? I think, yeah, I haven't really explored. I'm just kind of following the notebooks here. It'll touch on different encryption schemes in different bit length. He's saying I need to set this up. Okay, so my mistake was not initializing these parameters here. These parameters, scope type, platform, crypto target, simple serial version, these need to be initialized, and that was a mistake that I just made. So that's why this cell is empty, I am guessing. Alright, so I'm just going to copy this over here. So let me restart the kernel. Run this first cell block. Run the next cell block, and it should work. Yeah. Okay. The resolution was these 4 lines where we define and initialize the scope type, platform, crypto target, and simple serial version. Can you explain to me why exactly that was the resolution? What did it fix specifically? Are you able to provide that information for me? Or is it something we could ask Claude or Codex to inspect for us? I feel like there's a learning opportunity here, so I want to flag a product insight signal here, because I think configuring these variables is obviously very important. So I think it's something we should make sure that Trace Studios minimizes this friction point for students learning how to configure these variables and what they even mean. All right, let's ask our CLI agents to start working on manifesting this into the documentation. All right, now we're going to run the bash block here, and we get some build logs, and built in for platform CW Nano built-in target STM32 with crypto target set equal to tiny AES128C and crypto options set equal to AES128C. Provide a script for me that allows me to describe what these first 3 cells are doing, and to make it a script that I can use for a YouTube short later. It should be like less than 15 seconds and explained very well. All right. Let's do it. Let's do it. I'm using this as an opportunity to get shorts. So okay. And then I'm going to zoom in here. Yep, that looks good. All right. These first 3 cells set the stage for a real AES power attack. First, I'll tell Chipwhisperer I'm using the Chipwhisperer Nano with these 2 lines here. I'm using a Nano, Tiny AES, and Simple Serial version 2. I'm using a Nano, Tiny AES, and Simple Serial version 2. It connects to the device. Next, it connects to the device. Then, next, it connects to the device. Then, it compiles matching AES firmware for the target, ready to flash and measure power. What's going to take days to break AES? This device right here? Or are you saying me going through this lab experiment? Make it a little bit more engaging engaging of a script and explain a tad bit more technical detail. Yes, this all. Well, I'm breaking it tonight. This is getting broken by the end of the evening. Yeah, you're good, you're good. Yeah, you can just go. It's not a big deal. I don't have to. I mean, if you're going to be lingering around, let me know and I'll turn it off. But this is basically how things are going to go down tonight. I'm going to perform a correlation power analysis attack on a 32-bit microcontroller that is performing AES encryption, that's performing the computations for that encryption scheme. And I'm going to be deciphering the encryption key. That's what I think's going to be happening. I'm just also building a platform that allows for students like myself to learn how to do these kinds of things, maximize learning opportunity in a product that somebody can hook this up to and have a lot more pleasant of an experience with learning how to perform side channel analysis and understanding it and all the things that go into it, because so much of it is just setting up the environment. Before you even get to perform the experiments, you have to set up the environment, and that's like one of the biggest pain points, I think, with side channel analysis and this device itself. This is really easy now that I understand how to set it up, but at first this was a very difficult experience for me. I didn't even use it right away. It took me like a week figuring it out, trying it, couldn't get it, and then I put it away for a while, and then I picked it up recently and kind of realized like, oh, this isn't that difficult at all. So if there's anyone else out there who has similar pain points with this kind of stuff, I'm just documenting my journey and hopefully trying to connect with other people who find this stuff interesting as well. All right, so this cell block right here is not about compiling code. It's configuring the experiment. It passes 3 values into, oh my gosh. Right here, this cell isn't just about compiling code. It's configuring the experiment. It passes these 3 values into the make command call: the nano hardware target, the AES implementation, and the simple serial protocol. The compiler then builds a .hex firmware file image that has to match both the board and the host side capture setup. Get one wrong and your power traces may be useless. So if you get one of these wrong, the power traces may be useless. Platform, crypto target, simple serial version. Okay, cool. Maybe I can use that for sure. I don't know. I didn't really like the way that felt. Let's go ahead and do the next cell. All right, for firmware path. This is the firmware path. This is where the simple serial AES encryption exists in this file here. Firmware, MCU, simple serial AES, simple serial AES. We have a .hex file. And then we call chipwhisperer.program target. So this is basically finding the firmware implementation of AES, and then it is programming the target board with that firmware. So we're loading up that firmware to the target board, which is this guy at the very end of the device right here. So we are programming that target board with AES128, tiny AES128. Whatever that means. I don't know. Maybe it's like a less secure AES. What the? What's going on with this Python code? Can someone help me? Paste it into Discord as challenge to decrypt it. Oh, that sounds... Paste it into Discord as challenge to decrypt it. I'm curious what you mean by that. Are you proposing an idea for me to send to Discord? Like, try to decrypt this message or something. First person to decrypt this message. Something like that, or I'm not sure what you're suggesting. So we have a CW project 32-bit AES call. Right here. Module object is not callable. Not sure what that means. Please explain this Python code error. Post encrypted message, and yes, someone tries to decrypt it. Okay, let me think of something. Let me think of a challenge. That sounds fun. I like that. That's very clever. The capture cell stopped before any trace capture began. The capture cell stopped before any trace capture began. Okay, so what's the fix? Interesting. Provide me with a comment for this one line that I can put in the code block. All right. I wrote an encrypted chat room once. If you didn't enter the right passphrase, it wouldn't decrypt the room's message. That sounds like a fun little mini game. Maybe you can like spin up a game that it's based on encryption. Okay, so basically the hardware notebook is what you do before the actual lab just to confirm that your device can connect to all of the services that it needs to perform the experiment. So basically the hardware notebook is something that a student would use before they perform the actual experiment in the other main lab notebook. And so this seems like a product signal because it is a common best practice and should somehow be used in some way or considered. But this should just be marked as a product signal. I have a few Enigma examples of encryption and breaking the code. Yeah, I'm interested in most of security related topics, but I don't consider myself somebody who like understands all that much. I just have an interest and a passion for it, and I want to learn about it. And I don't know what I don't know. All right, now provide a pass-off report that I could give to the next Comet browser assistant. I have a few yet. All right, I gotta use the restroom, so I'll be right back. I have a few engine. Yep. All right, let's pass this over. We're now going into the main hardware notebook. Where are we going? Yep, the main. We're going now to the main CPA on 32-bit AES notebook. Alright, this music isn't really the vibe right now. So, let's go back to some original. Alright, here we go, guys. Look at this. Optimizing AES. We have an S box where we pass in the state, and that's equal to the S box of this 4x4 matrix. I'm not sure if, I think each of these are bytes, because there's 4 times 4 is 16, and each of these contain 4 bits. I don't think that adds up, but we'll get to that. All right, so let's go ahead and paste the browser assistant passover. The visible main notebook confirms the intended experiment is correlation power analysis attack on MBED. What is this? Explain what MBED TLS is. I don't understand it. This is a product signal. We should be able to provide information for students that inform them on stuff like this. Where you guys at? Where you guys at? Embed TLS is a cryptographic software library, a collection of code that lets embedded. All right, let's zoom in a little bit. Embed TLS is a cryptographic software library. It is a collection of code that lets embedded devices perform operations such as AES encryption, TLS/HTTPS security, hashing, and key exchange. In this lab, it is the specific implementation of AES running on the target board, not a different encryption algorithm. In lab terms, AES is the standardized encryption algorithm. Tiny AES128C and Embed TLS are two different code bases that implement AES, so they produce the same correct ciphertext for the same key in plaintext, but they can execute very differently on a microcontroller. So here's what we're doing in this experiment. AES is the encryption algorithm being attacked. Tiny AES128C is a simpler generic AES implementation used in the earlier labs. Embed TLS is a broader embedded security library whose AES code is optimized for 32-bit machines, and CPA, the attack method, which correlates predicted interval values with measured power traces. The notebook says Tiny AES128C does not use implementation-specific optimizations, whereas Chipwhisperer Embed TLS implementation uses a 32-bit t-table, which uses 32-bit t-tables. A t-table is pre-computed lookup table. Rather than separately computing AES's sub-byte shift rows and mix columns operations byte by byte, Embed TLS can combine them into lookups of 32-bit values plus XOR operations. The lab describes four tables of 256 entries each, occupying 4 kilobytes total when stored as four 32-bit values. A helpful analogy. Both implementations solve the same math problem. Tiny AES does more of the arithmetic step by step. Embed TLS keeps a set of pre-computed answer sheets and looks up 32-bit chunks, trading memory for speed. Why does this change the traces? The notebook says Embed TLS is faster and that an entire encryption can fit into fewer than 5,000 samples, where the earlier Tiny AES capture had reached only partway through round 2 in the same window. It also says individual AES rounds are harder to visually distinguish in an Embed TLS power trace. That is why I captured AES traces. It is not enough provenance for this lab. The implementation determines the timing, instructions, memory accesses, and therefore the waveform shape and leakage behavior. The lab says correlation power analysis can still use the familiar AES S-box output leakage model because the two t-table lookups depend on the S-box key XORed by the plaintext, the same first round relationship used in the earlier attack. So the core CPA idea remains: guess the key byte, predict an internal AES value, and then correlate with measured power. But the target's optimized implementation means the relevant activity is compressed and may include leakage from 32-bit table values, motivating the notebook's later t-table leakage discussion. The lab introduces Embed TLS only after earlier work with Tiny AES128C, then immediately asks learners to capture 100 Embed TLS traces and interpret a more complex waveform. A student facing pre-flight should make this explicit before build and capturing. What is it? Embed TLS and the AES software implementation used for this experiment. Why is it selected? This lab studies 32-bit t-table optimization, not merely AES correctness. What changes? Expect faster, denser traces and less visually separable rounds. Why it matters for analysis. Use the dataset only with an analysis path intended for selected firmware implementation. How to verify it. Show the resolved firmware target, build output, firmware hash versions, and trace project provenance. One question. Your current hardware build output established Tiny Tiny AES128C, not Embed TLS. We still need the hardware notebook's stated CW Nano supported target configuration before concluding how this lab should be acquired on your setup. That was a mouthful. I just read a whole bunch. It was very helpful information. So I should just replace the crypto target Tiny AES128C with Embed TLS. All right, so now we have Embed TLS. Embed TLS is now our crypto target, so we're no longer using Tiny AES128C. All right, now we're programming the device. Okay, it's been verified and it works. Now we're capturing the 100 traces. Okay, now we go back. All right, so far we've been focusing on a single implementation of AES, which is the Tiny AES128C, or the AVR crypto lib, if you're using an XMega. Tiny AES128C, which is designed to run on a variety of microcontrollers, doesn't make any implementation-specific optimizations. In this lab, we'll look at how we can break a 32-bit optimized version of AES using a CPA attack. In this lab, we expect to have a better understanding of how AES can be optimized on 32-bit platforms, and how attacking an optimized version of AES, and how to attack an optimized version of AES using correlation power analysis. Optimizing AES. A 32-bit machine can operate on a 32-bit machine can operate on 32-bit words. So it seems wasteful to use the same 8-bit operations. For example, if we look at the SBox operation, B is equal to SBox with some state, and that is equal to okay, so the SBox transforms this matrix. We could consider each row as a 32-bit number. So each of these elements contain 8 bits. So each of these elements are a byte. S0, S4, S8, and S12 are 32-bit numbers and do 3 bitwise rotates instead of moving a bunch of stuff around in memory. We can speed up AES considerably by generating 32-bit lookup tables called T-tables, as we described in the book as described in the book, The Design of Rindal, the AES, the Advanced Encryption Standard. $104. So the design of Rindale speaks on T-tables. In order to take full advantage of our 32-bit machine, we can examine a typical round of AES, with the exception of the final round. Each round looks like this. A is equal to the round input, B is equal to the sub-bytes, and C is equal to the shift rows, D is equal to mixed columns, and there's a certain way to A something, the derivative of A, I don't know how I would say that term, I forget. I want to say A prime, but is equal to add round key, which is equal to the output. We'll leave the add round key the way it is. The other operations are B sub I sub j is equal to the S box of A sub I sub j. Okay. So B is equal to the S box of A, which is equal to j plus 1 plus 2 plus 3, which is equal to note that the shift rows operation is a cyclical shift, and the matrix multiplication in mixed columns denotes this is a critical product signal. This type of comprehension mathematically requires the immersive experience that allows a student to learn about this particular branch of mathematics and to have this section explained in sufficient detail. Let's go ahead and provide a prompt back to the main Perplexity project space so that we can properly pass over all the information from all of the different assisters. Man, I must be getting tired or something because I'm a little overwhelmed by this notebook, I guess. I added 4 new cells after the math explanation, and I'm wondering if these are the correct cells to have ran. And I changed tiny AES128C to embed TLS. Is this what I need, or should I just run the CW plot project waves cell? As you can see, I changed the first 3 cells because I think it's a better way of doing things. I referenced the solution notebook to find that. Okay, now explain this graph to me and what it means based on the text that describe it. ELI 10 everything we have done thus far up to this point and make the script something that can be referred to later when making YouTube shorts during this live stream. Alright, so today we used a Chipwhisperer Nano to watch a tiny computer encrypt data with AES. First, we chose a hardware configuration. The Nano board, its built-in STM32 chip, and the simple serial protocol. Then we compiled an AES program and flashed it onto the chip. Flashing is basically installing our encryption program onto a tiny computer. Next, we told the board to encrypt lots of different known messages while we measure tiny changes in its power use. Every encryption makes a squiggly line called a power trace. The left to right direction is time. The up and downward movements is a measurement related to how the chip's power changes while it works. We collected 100 capture attempts and saved them as a trace project. But this is important. 100 attempts does not automatically prove we save 100 good traces. The code can skip failed captures. Then we plotted one trace. The graph does not show the secret key. It does not mean the AES is broken. Then we plotted one trace. The graph does not show the secret key. It does not mean AES is broken. It's simply a record of the electrical activities while encryption happened. The next step is called correlation power analysis. We make 256 guesses for one secret key byte. We predict what the chip might calculate for each guess, and we check which prediction matches the power traces best. The surprising part is that we do not need to visibly point to every AES round in the graph. Statistics can find a consistent data-dependent pattern across many traces. Our goal is to not look at a squiggle and guess the key. Our goal is to make a mathematical prediction, compare it against many measurements, and see which key guess best explains the evidence. What does the lab expect from me as the student to already know, because it is not providing me with this cell filled with the solution? The lab experience that we're creating with Trace Studios need to be able to prepare students and users and help them understand how to write these functions and how to make these calls for this particular kind of solution creation. Since we expect students to be able to do this stuff on their own, we need to be able to provide an experience that introduces them to the practice of writing this kind of code. Now explain in a script-friendly way what we have done to lead up to this cell and what this cell is doing. Spend more time on what this cell is doing. Okay, so up to this point, we have been building an experiment, not breaking AES by looking at a graph. Okay, so up to this point, we have been building an experiment, not breaking AES by looking at that graph. First, we configured the Chipwhisperer Nano and its built-in microcontroller target. Then we compiled and flashed an AES program onto that tiny chip target. Next, we repeatedly gave the device known messages to encrypt and measured tiny changes in its power while encryption ran. Next, we repeatedly gave the device known messages to encrypt and measured tiny changes in its power use while encryption ran. Each recording is called a power trace. We collected many of them because one trace is noisy. But a repeated mathematical pattern across many traces can be measured statistically. We then plotted a trace. That squiggly line is not the key, and it is not a direct picture of an AES round. It is a timeline of the target's electrical activity. The graph gives us something to inspect. But the actual attack comes from comparing many traces against many mathematical predictions. Now we are at the correlation power analysis cell. This short cell is where we turn our collected measurements into a statistical key guessing experiment. The first line imports the Chipwhisperer analysis toolbox and gives it the short name CWA. The second line is the most important decision in this cell. Leakage model. We set that equal to the t-table. A leakage model is our mathematical story about what the chip might be doing internally, and what part of that internal work might slightly affect its power use. We are not telling the program the secret key. Instead, we tell it, for every possible key byte guess, predict the value that this specific AES implementation would process, then see whether that predicted value matches changes in measured power. Earlier, a basic model would predict only the AES S-box output, but this lab describes embed TLS as using something called a t-table. A t-table is basically a pre-computed cheat sheet that lets AES process a bigger 32-bit bundle of information at once. For each input byte, the implementation uses an S-box value twice, plus versions of that value multiplied by 2 and by 3 using AES's special math. The lab describes the predicted leakage as the combined number of 1 bits in that whole table-derived value. Instead of guessing how much power the chip might use for every one tiny 8-bit AES value, we are guessing how much power it might use for the bigger 32-bit value produced by the t-table implementation. That's why the model is called t-table. It tries to match our math to the actual way this version of AES is implemented on the device. Okay, so then this next line creates the attack, where attack is equal to the Chipwhisperer analyzer where attack is equal to CWA.CPA of our project traces, where we pass in our project of traces and the leakage model that we're using. Project is our evidence folder. It holds the saved waveforms, the power traces, as well as the known plaintext and other capture data attached to those traces. Leak model is our prediction rule. Put together, this line tells Chipwhisperer, take this collection of power traces and test them using this t-table prediction model. At this stage, nothing has run yet. We have only assembled the experiment, the measurements on one side and the mathematical theory on the other. The final line actually starts the analysis. Correlation power analysis works one key byte at a time. for a particular key byte position, it tries every possible value from 0 through 255. For each guess, it uses the known plaintext byte from every trace. It combines the known plaintext with the current key guess, predicts the related t-table leakage value, and counts its 1 bits. That gives the attack one long prediction list per key guess. This is a long script. Let's just run the thing. All right, we ran the cell, and now we are being asked, did this attack work better than the previous one? Okay, now that we have finished the lab, provide a full recap of this session so that we can pass it back over to the main perplexity space. I think perplexity got stuck. There it goes. Please finish the response. Try again with browser control. I switched it from tiny AES128C to embed TLS. Yes, I did finish it. You can see down here at the bottom, this is where we had deciphered. Right here in this red text. Explain what this red text is here. Okay, so this red text is the output style for the Chipwhisperer, and the red is the top ranked key byte candidate row. It's the tool's way of visually highlighting what is currently being considered, what it currently considers each byte position's best guess. What the table structure means. The table has columns 0 through 15, 1 per AES128 key byte. That's a key byte of 128 bits. Yes, correlation power analysis, CPA. Explain correlation power analysis. The correlation power analysis attack is a side channel attack that recovers a secret cryptographic key by statistically comparing predicted power consumption against measured power consumption. A side channel attack that recovers a secret cryptographic key by statistically comparing predicted power consumption against measured power consumption without ever directly reading the key from the device. A microcontroller's instantaneous power that is drawn depends slightly on the data it's processing. Moving a byte with many 1 bits typically draws marginally different current than moving a byte with few 1 bits. Correlation power analysis exploits this by testing many hypotheses about a secret key byte and seeing which hypothesis predicted power pattern best. Which hypothesis's predicted power pattern best matches what the Chipwhisperer actually measured across many encryptions. The 4-step process: collect many traces with known plain texts. For each encryption, the target receives a known plain text, uses a fixed unknown key, and produces a power trace, which is a series of voltage variation samples over time. This is the project object being passed into the attack in the visible cell. And what device you attacking? Has it got masking built in? I'm attacking this device right here. If you can see it on the camera. This is the Chipwhisperer Nano device. It has a target board and a scope board on this one board. And the target board is performing the encryption, and the scope board is measuring the power consumption of that target board that's performing the encryption. And we're trying to decipher the cryptographic key by measuring the changes in voltage with respect to time, and then identifying patterns, and then making guesses at what the key is, and using a large sample of traces different power traces that were collected by that target. So you scan the target as it's performing the encryption. You measure the power changes over time as that board is performing the encryption. And then you get a large sample of traces from that board. And then you try to find patterns in the traces. And so you're not even like interacting with the device. You're accessing a side channel of information. You set it up to attack itself. It's a small open source beginner side channel analysis tool chain. So yeah, it has a target board and a scope board, and it's a really small device that you can perform these attacks on. You can get bigger, more expensive setups and devices and attack another device that's external to it and not attached. You can actually detach this board right here. You can break it off, and you could then attach it to another kind of you can configure it to another piece of hardware. You can do something with it, I don't know, but it's sort of like a learner device. Yes, rather than deciphering, you're robbing the guard of his key. A side channel. Electromagnetic fields. Measuring fluctuations in EM fields. Okay, so the 4-step process is to collect many known traces with known plain texts. Guess one key byte at a time. Rather than trying all 2 to the 128th power possible AES keys all at once. What is 2 to the power of 128? What is 2 to the power of 128, and how does it relate to AES encryption?
2 to the power of 128 is an extremely large number, approximately 340 undecillion. In AES encryption, this number represents all the possible combinations for a 128-bit secret key, making it virtually impossible to crack with regular computers.
How does side channel analysis create potential vulnerabilities? This is the number of keys, different value keys. I don't even know how to say that number. Collect traces, guess key bytes, predict leakage using a leakage model, and then correlate predictions against every sample. I want this to be a product signal that there should be a more interactive and visualize this kind of I want this to be a product signal because I think it's important to be able to take a user through some kind of interactive experience where they can visualize as well these different kind of subject matters coming together, like math and statistics and encryption and Python and code writing. I think we need to be able to bring this all together in the experience to teach people how to use these various tools that are being brought together here. All right, let's provide a follow-up pass over back to the main Perplexity project space. All right, now let's communicate with Claude and Codex to start scaffolding some kind of infrastructure. I think it's important to have some kind of graphical user interface to interact with. So we need to start making decisions about what kind of environment we want to create and what dependencies will be involved. And it's really important to understand that so that we can configure all the existing Chipwhisperer dependencies and product signals that we've already mentioned before. And the considerations about the code and which code we should use to write this application needs to be considered as well. The first real user would be somebody who decides that they're interested in learning about side channel analysis and how they can start practicing and learning whatever skill sets are necessary to begin performing their own research and being able to interact with these tools. Specifically, the Chipwhisperer Nano device should be the kind of starting point most people will enter, and then eventually down the line, more robust and expensive tools that Chipwhisperer has as well. I want version 1 to obviously work for my MacBook so that I can use it as well. I'm not sure if I want SCA 201 as the main focus. I kind of want to build things from the kernel level up of this service and make sure all of the hardware and libraries and dependencies can be configured before we start including labs and projects and features and functions. We should have a very early stage platform, very simple, not much graphical user interface other than the necessary to understand the system. I don't really think Jupyter Notebooks is something I want. There are some useful things you can do in Jupyter Notebook, but I want to rethink the approach for performing experiments and reshape how learning opportunities are introduced. V1 should not embed or coordinate any existing notebooks right now. The only UI focus right now is to just get some kind of basic window that shows the hardware is connected and any kind of dependency configuration for the environment should be setting up user interface type of stuff. I think we should start educating the students on how to write Python code specifically for performing attacks. I think that is one learning outcome I would like for the students to have. Additionally, the program should have features that allow for less code intensive experimenting. There should be environments that allow a user to perform experiments by writing code, but there should also be other environments that do not involve so much code writing, and that there are dials and knobs and controls that are embedded in the lab environment within the Trace Studios application, given certain project scopes. So I think for the Chipwhisperer execution, we should still be making considerations about the different decisions we can make. I'd like to consider making it cross-platform, but I also want to evaluate the advantages of making it native to macOS for right now. But I feel that having a larger audience would be the best long-term, and it might be better to just start off that way rather than trying to do that part later. I think we need to have a conversation in depth about the bundled versus detected externally. I'm not sure what the source of truth would be for the experiments. We should talk about that more. We should consider different learning assistants and student agency preservation ideas. Let's not make a decision about that right now. I'm not sure on distribution and trust model right now. I just want to build this and see how it evolves. Propose a few ideas for what might constitute a successful V1, and I will choose which one I think is most accurate. I even might want to include an environment for learning where a user can explore the actual hardware platform itself in sort of this graphical, appealing landscape type of way, three-dimensionally, can inspect sort of the circuitry and zoom in on the devices and all of the electrical components on the device as if it were you as a small particle able to scan these electrical components and see them and how they're working and see maybe even their logic gates. But that might be a little bit too complex. But some kind of environment where the user can explore the hardware, because this is appealing to circuit analysis, comprehension, and electrical engineering related thoughts. Let's see how that does. All right, given today's workflow session and the completed lab experiment, how can we prompt codecs and flawed CLIs to start working with us to achieve our vision? Right, so that was the experiment. I think I'm going to go ahead and end the stream now because at this point I'm no longer performing the experiment. I've already completed it. I'm just building the software part of this experiment, this project now, I guess. Trying to build a system that allows me to perform these experiments, but better. So we're sort of getting to the tail end of the stream. Still going. Alright guys, thank you so much. I'm going to go ahead and end it now because we are done with the experiment. So stay tuned. The next one should be good.